This is another short section. Again, I do not anticipate you having to do any of these calculations. You'll see what I mean as we go through, but I want you to be aware of the energy changes that are involved in a nuclear reaction. I've always wondered, where does the energy come from? And it wasn't until I taught Gen Chem that I actually could see. And then I always wondered, like when you see a mushroom cloud, why is there so much energy? Why is it there? Well, unlike a chemical reaction where we're making and breaking bonds, what we're doing here is we're rearranging protons and neutrons. I know that sounds very much like science fiction, but it all starts with Einstein's equation. E is equal to mc squared. You've probably seen it before. M is equal to mass, and that's the lost mass in an exothermic reaction. Speed is the same old speed of light that we've seen before. It is a very large number, so it involves a lot of energy. So when people talk about nuclear reactions, they often talk about something called a mass defect, and that just means a delta M. It is used to calculate the energy that is released. Another term they use is a binding energy. You'll see that on the last slide in this little video, and it's how much matter that would be converted into energy and released if the nucleus were formed from initially separate protons and neutrons. Again, information only. So the two slides that follow this are going to talk about Einstein's equation and the amount of energy involved. We've done the hydrogen balloon demo many, many times in class, and I'll just have to send a video so that we can have it at our last lecture. So if you do that same old boring hydrogen balloon demo, you've got hydrogen gas in the balloon, there's oxygen gas in the air, someone walks up to it with a lit candle, and essentially we're producing water. Angie tells us to cover our ears, and we hear a big boom and see a flame. Well, if you do that calculation, that reaction involves a mass change of minus 12 kilograms. That is an extremely small mass change that occurs during a chemical reaction. Now, let's contrast. This is the most, I found this so interesting when I started teaching Gen Chem. How much energy could you get if you were to split an atom? Chlorine, you know, that's that diatomic molecule. It's also an atom. But if you use its values in this calculation, which no one in this class will ever do, what you come out with is a much different value. 10 to the 13th kilojoules of energy. And I like this analogy. That is enough energy to heat 76,000 tons of water from 0 to 100 degrees instantly. So that kind of gave me a better idea of when I see a nuclear explosion, what's being involved. And when someone does fission of 1 mole of uranium-238, what they get is 4 times 10 to the 8th kilojoules. Oh, I think that should be uranium-235. But we will just say, let's just call it uranium, okay? It's the end of the term. Last slide in here. I just want to make you aware of something called a nuclear binding energy. You can see mass number is rolling along the x-axis, and something called binding energy is rolling along the y-axis. So when people do fission, that's when you split a nuclei. When people do fusion, you combine nuclei to release energy. The word is, the greater the binding energy, the more stable the element. And those are the elements we have between, say, 40, which is here, and 150, which is here. Again, all of this was just knowledge. No one's going to test you on it, but it's part of understanding what happens in nuclear chemistry.